how many galaxies exist in our universe? At first glance, the question feels almost casual. The kind of thing you might ask while looking at a photograph of the night sky or reading a headline about a new telescope discovery. It sounds like a question that should have a tidy answer, a number you can write down, remember, and move on from. But the moment you try to sit with it, the question begins to unravel. It stretches beyond intuition, beyond language, beyond the mental tools your brain evolved to use. What starts as curiosity quickly turns into something more destabilizing, because the answer is not just large. It is so large that your mind has no natural way to hold it. We live our lives surrounded by numbers that feel big to us. 1,000. People in a crowd feels overwhelming. $1 million feels abstract, but still imaginable. Even 1 billion, though difficult, can be placed into some mental framework with effort. But galaxies are not counted in thousands or millions or even billions in any comfortable sense. The scale involved here leaps so far beyond everyday experience that the usual mental shortcuts stop working. You can repeat the number out loud, you can write it down. But none of that means you truly understand it. This is where the question begins to matter. Not because of the number itself, but because of what happens when your intuition fails. The universe does not scale down to meet human understanding. It does not pause to make itself comprehensible. Instead, it confronts us with quantities that feel almost hostile to intuition, forcing us to rely on abstract reasoning rather than instinct. When astronomers talk about the number of galaxies, they are not just describing a cosmic inventory. They are revealing a gap between what exists and what the human mind can naturally elant. We have to accept that our emotional sense of size and number is unreliable. We evolved to navigate small groups, short distances, and immediate threats, not to comprehend structures spanning billions of light years. When we hear a number tied to galaxies, our brains try to compress it into something familiar, something manageable. That compression always fails. The failure is not a weakness of intelligence. It is a mismatch between evolved intuition and cosmic reality. There is also a deeper discomfort hiding in this question. We like to believe that the universe, at some level, is understandable in a way that feels satisfying. We expect that if we gather enough data, build better instruments, and think carefully enough, the answers will eventually settle into something stable. But the number of galaxies refuses to sit still. It shifts as our methods improve, as our perspective deepens, as we realize how much of reality has always been invisible to us. Each apparent answer carries within it the implication that we are still missing something. That realization creates a kind of cognitive tension. On one hand, science is extraordinarily successful. We can measure distances across the cosmos, trace the history of galaxies, and model the evolution of the universe itself. On the other hand, the simple act of counting reveals how incomplete our view remains. The question how many galaxies exist is not just about abundance, it is about limits. Limits of observation, limits of knowledge, and limits of intuition. As you follow this question, you begin to see that the number is not meant to be comforting. It is meant to unsettle. It reminds us that the universe is not built to fit neatly into human categories. It resists being reduced to something emotionally digestible. And yet, we ask the question anyway. We insist on counting, measuring, and estimating, even when the results defy our ability to truly feel what they mean. This is the tension that will guide everything that follows. We are going to talk about numbers that cannot be visualized, distances that cannot be traveled, and quantities that cannot be internalized. The goal is not to make these ideas feel small or familiar. It is to understand why they refuse to do so. It's because in that refusal lies something important about our place in the universe, and about the strange power of human curiosity. We may not be able to emotionally comprehend how many galaxies exist, but we can still understand why the question matters, and why it keeps pulling us deeper into a reality far larger than anything our intuition was designed to handle. The human extraordinary tool, but it was never designed for the universe we now try to understand. It evolved in environments where survival depended on navigating immediate surroundings, recognizing familiar faces, tracking small quantities, and reacting quickly to nearby threats. For hundreds of thousands of years, the most important numbers in human life were small. How many people were in your group? How many days of food you had left? How many animals were moving through the grass? These were numbers you could see, feel, to respond to without abstraction. This evolutionary history shaped how we intuitively understand quantity and scale. We are remarkably good at estimating small numbers at a glance. Do not need to count to know the difference between 3 objects and 5. You can sense when a crowd grows too large to manage or when resources feel scarce. But this ability drops off rapidly as numbers increase. Once quantities climb beyond a few dozen, intuition gives way to approximation. Beyond a few hundred, intuition largely disappears. Numbers become symbols rather than experiences. This is not a flaw. It is an adaptation. A brain optimized for cosmic scales would have been useless on the African savanna. There was no survival advantage in grasping millions or billions when daily life unfolded within a few kilometers and a few dozen social relationships. As a result, our sense of scale is deeply local. It is grounded in bodies, landscapes, and lifetimes, not in light years or cosmic volumes. Because of this, we rely heavily on metaphor and analogy when confronting large numbers. We break them into time-based comparisons, spatial metaphors, or repetitive actions. We say things like imagine counting 1 per second, or stretch this distance across the Earth. These techniques are not explanations in the strict sense. They are coping mechanisms. They allow the brain to anchor abstract quantities to familiar experiences, even though the anchor is always inadequate. When we shift from tribal scale thinking to cosmic scale reality, the mismatch becomes obvious. A tribe might number a few dozen individuals. A large ancient city might hold hundreds of thousands. Modern nations count their populations in the millions. Even these scales strain intuition, but they are still tied to human experience. Galaxies are not. They are not just larger communities or distant cities. They exist on a scale that has no natural reference point in human life. This gap forces an identity shift. We like to think of ourselves as capable of understanding our surroundings. As intelligent agents living in a knowable world, cosmic numbers challenge that self-image. They reveal that understanding does not always mean feeling. You can know a number is correct without having any emotional grasp of what it represents. That realization can feel uncomfortable because it undermines the idea that comprehension is always intuitive. Yet there is also humility in this recognition. Accepting the limits of intuition does not diminish human intelligence. It clarifies it. Intelligence is not the same as instinct. Instinct is inherited. Intelligence is constructed. Where instinct fails, we build tools. Mathematics exists precisely because intuition breaks down. It allows us to reason reliably about things we cannot picture or feel. Trust in science depends on this distinction. When astronomers talk about scales far beyond human experience, they are not claiming special perception. They are relying on methods that compensate for our cognitive limitations. Measurements, equations, models, and repeated observations form a scaffold that supports understanding where intuition cannot reach. The confidence we place in these methods is not blind faith. It is earned through consistency, prediction, and verification. This is why discussions of the universe often feel both empowering and humbling. Empowering because we can describe realities far beyond our evolved senses. Humbling because doing So requires admitting that our natural intuitions are insufficient. The universe does not feel large to us in any meaningful, emotional sense. It feels abstract, distant, and strangely impersonal. And that is exactly what we should expect from a brain shaped by local concerns. Understanding this helps reframe the question of galaxies. The difficulty is not that the number is unknown or uncertain. The difficulty is that even a perfectly accurate number would not feel real. It would still live outside the space where intuition operates. The discomfort comes from expecting the universe to align with the way our minds work, rather than the other way around. Once this expectation is released, something interesting happens. The failure of intuition stops being frustrating and starts being informative. It tells us where biology ends and where deliberate reasoning begins. It reminds us that our view of reality is not default or complete, but constructed through effort and collaboration across generations. In that sense, cosmic scale is not an enemy of understanding. It is a mirror. It shows us what kind of creatures we are, what our limits are, and how far we have learned to reach beyond them. We may never feel what a trillion truly means, but the fact that we can reason about it at all is evidence of a different kind of strength, not the strength of instinct, but the strength of curiosity, disciplined by method. When we galaxies exist, we have to be precise about what we mean by the universe itself. The word sounds all-encompassing, as if it refers to everything that exists, everywhere, without exception. In everyday language, that is usually what it means. In cosmology, however, the universe we talk about is defined in a far more careful and constrained way. What astronomers usually mean is the observable universe, and that distinction changes the entire question. The observable universe is not the whole universe. It is the portion of reality that we can, in principle, observe from Earth. That limitation is not primarily a matter of technology. It is not simply that our telescopes are not powerful enough. Even with perfect instruments, there would still be a boundary beyond which observation is impossible. That boundary exists because the universe has a finite age and because light, while incredibly fast, does not travel instantaneously. Light moves at a fixed speed, about 300,000 kilometers per second. That speed feels absolute in human terms, but the universe is vast enough that even light needs time to cross meaningful distances. When you look at the sun, you are not seeing it as it is right now. You are seeing it as it was 8 minutes ago, because that is how long its light takes to reach Earth. The farther away an object is, the farther back in time you are seeing it. Distance and history are inseparable. The universe itself began about 13.8 billion years ago. That means there has only been 13.8 billion years for light to travel since the beginning of everything. At first glance, you might assume this limits what we can see to a sphere with a radius of 13.8 billion light-years. But the universe complicates this picture because space itself has been expanding the entire time light has been in transit. As light travels, the space it moves through stretches, increasing the distance between where it started and where it ends up. When this expansion is accounted for, the observable universe turns out to be much larger than 13.8 billion light-years across. In fact, it has a diameter of about 93 billion light-years. That number already strains intuition, but it represents a very specific idea. It is the region from which light has had enough time, despite cosmic expansion, to reach us since the beginning of the universe. Everything inside that boundary is observable in principle. Everything beyond it is not. This boundary is sometimes called the cosmic horizon. It is not a physical wall or edge. Nothing special happens there. Galaxies do not suddenly stop existing. The horizon simply marks the limit of what information can reach us. Beyond it, light has not arrived yet and may never arrive because the expansion of space can carry distant regions, away faster than light can bridge the gap. This introduces a subtle but profound point. The observable universe is not growing because we are seeing farther in space. It is growing because time is passing. As the universe ages, light from more distant regions has time to reach us, gradually bringing new areas into view. At the same time, accelerated expansion means some regions will always remain out of reach, no matter how long we wait. The observable universe is a moving window, not a fixed container. When astronomers estimate the number of galaxies, they are always talking about galaxies within this observable region. They are counting only what lies inside the cosmic horizon. They are not making claims about the total number of galaxies that exist everywhere, because that number may be vastly larger, or even infinite. The observable universe is a sample, albeit an enormous one, drawn from a reality that extends beyond our reach. This distinction matters because it shapes how confident any number can be. A count of galaxies in the observable universe is constrained by physical law, not by ignorance. It is the best that can be done from our position in space and time. Any statement about the full universe requires additional assumptions about uniformity and structure beyond what we can observe directly. There is also an important psychological effect here. The phrase observable universe quietly reminds us that reality is larger than our access to it. No matter how advanced our science becomes, there will always be parts of the universe that are causally disconnected from us. This is not a temporary limitation waiting to be solved. It is built into the structure of space, time, and expansion itself. Understanding this reframes the original question. Asking how many galaxies exist is not just a matter of improving measurements. It is a question bounded by fundamental limits. We can refine our estimates within the observable universe, and we will continue to do so. But beyond that horizon lies a vast unknown, not because we lack curiosity, but because the universe does not allow information to flow freely everywhere. The observable universe, then, is not a compromise or a second-best answer. It is the arena in which all empirical cosmology takes place. It is the largest stage on which evidence can appear. When we speak with confidence about galaxies, distances, and cosmic history, it is within this defined domain. Beyond it, we can reason, extrapolate, and speculate. But we cannot observe. This realization adds depth to the question, rather than limiting it. It tells us that when we count galaxies, we are not just tallying objects in space. We are mapping the reach of information itself. The number we arrive at is not simply about abundance. It is about what the universe has allowed us to know so far, and about the vastness that still lies beyond the horizon, silent, unseen, and unconstrained. By our questions, when we universe, we are never seeing things as they are right now. We are always seeing the past. This is one of the most counterintuitive but essential ideas in astronomy. And it reshapes how we understand everything from distant galaxies to our own place in cosmic history. The reason is simple in principle, but profound in consequence. Light takes time to travel. Light moves incredibly fast, faster than anything else in the universe. Yet even at that speed, it cannot overcome the vastness of space instantly. A star emits light. Those photons begin a journey that may last minutes, years, or billions of years before reaching an observer. By the time they arrive, the source that emitted them has already changed. In some cases, it may no longer exist at all. The most familiar example is the sun. The light warming your skin on a bright day left the sun about 8 minutes earlier. If the sun were to vanish at this moment, we would continue to see it shining peacefully in the sky for 8 more minutes, completely unaware that anything had happened. Even within our own solar system, observation is delayed by time. The universe never presents itself live. As we look farther away, this delay grows. Light from the nearest stars outside the solar system takes years to reach. Earth light from nearby galaxies takes millions of years. When we observe the Andromeda galaxy, we are seeing it as it was roughly 2 million years ago, long before modern humans existed. The galaxy we see tonight is a snapshot frozen deep in the past. At larger scales, this effect becomes staggering. Light from very distant galaxies has been traveling for billions of years. Those photons began their journey when Earth itself was radically different. In many cases, they left their source before complex life had evolved, before plants colonized land, before animals existed at all. The deeper we look into space, the further back in time we are forced to look. This means astronomy is not just the study of distant places. It is the study of ancient eras. Every telescope is also a time machine, revealing earlier chapters of cosmic history. The night sky is not a single moment spread out across space. It is a layered record composed of light emitted at countless different times, all arriving here now. This perspective transforms how we interpret what we see. A distant galaxy is not simply far away. It is young. Its structure, color, and behavior reflect conditions that no longer exist in the present universe. When astronomers study galaxies at different distances, they are effectively watching the universe evolve. Nearby galaxies show us how galaxies behave today. Faraway galaxies show us how they behaved billions of years ago. In this sense, observing the universe is closer to archaeology than photography. An archaeologist does not observe an ancient civilization directly. They reconstruct it from fragments left behind, interpreting layers of evidence formed at different times. Astronomers do the same, except their artifacts are photons instead of pottery shards. Each photon carries information about the conditions under which it was emitted. The deeper the observation, the older the layer being uncovered. By studying galaxies at increasing distances, astronomers can piece together a timeline of galaxy formation and evolution. They can see when the first galaxies formed, how quickly stars were born, how structures grew and merged, and how the universe gradually transformed from a simple state into the complex cosmic web we observe today. This temporal layering also means that the universe we see is inherently incomplete. The most distant regions we can observe show us the universe when it was young, not as it is now. Those galaxies have continued to evolve during the billions of years their light has been traveling. Their present state is hidden from us, unreachable, until new light arrives far in the future. At the same time, there are regions whose light has not yet reached us at all. These regions exist right now, but they are invisible because their photons are still en route. In some cases, due to cosmic expansion, their light may never arrive. The observable universe is therefore a record of the past. It's not a full map of the present. This has a subtle psychological effect. We are accustomed to thinking of observation as a way of accessing reality directly. In everyday life, seeing feels immediate and reliable. In cosmology, seeing is always delayed. Every observation comes with an intrinsic timestamp, and that timestamp grows older with distance. Reality, at cosmic scales, is something we can only ever encounter indirectly. Yet there is also something deeply awe-inspiring about this limitation. When we look at distant galaxies, we are not just seeing objects. We are witnessing history in motion. The light entering a telescope tonight may have left its source when the universe was a fraction of its current age. It has survived billions of years of travel through expanding space, carrying information across unimaginable distances. Just to arrive here, this means the act of observation itself is extraordinary. The universe has left a record of its own past, written in light, and that record is accessible to us. We can reconstruct events that happened long before Earth formed, not through speculation, but through direct evidence encoded in photons. Understanding light travel time forces a shift in perspective. space and time are no longer separate ideas. Distance becomes a measure of age. Looking outward becomes looking backward. The farther we push our instruments, the deeper into cosmic history we peer. This is why counting galaxies is inseparable from understanding time. Each galaxy in our surveys occupies not just a position in space, but a position in history. The total number we estimate reflects not only how many galaxies exist, but how many have existed across different eras of the universe. When we ask how many galaxies there are, we're implicitly asking how much of the universe's past we can see. The answer is not static. It depends on how far back our observations reach and how clearly we can interpret the faintest, oldest light. In that sense, galaxy counting is not just a census. It is an excavation of time itself, an ongoing effort to read the universe's history from the fragile ancient light that continues to arrive moment by moment from the depths of space. At first, a galaxy feels well-defined. Most people picture a majestic spiral of stars, glowing arms wrapped around a bright center, suspended in the blackness of space. That image is familiar, comforting, and deceptively simple. It suggests that galaxies are obvious objects, easy to recognize and easy to count. But once you move beyond intuition and into the details, the idea of what qualifies as a galaxy becomes surprisingly slippery in its most basic form. A galaxy is described as a gravitationally bound system of stars, gas, dust, and dark matter. Gravity is the key word. A galaxy is not just a loose collection of stars drifting together by chance. It is a structure held together by its own mass, moving as a coherent unit through space. This definition sounds precise, but it quickly runs into trouble when applied to the real universe. The first complication is scale. Galaxies exist across an enormous range of sizes and masses. Some contain hundreds of billions or even trillions of stars. Others contain only a few thousand. The largest galaxies can span hundreds of thousands of light years. The smallest can be smaller than many star clusters found within larger galaxies. If size alone determined what counts as a galaxy, the line would be arbitrary. Nature does not provide a clean cutoff. Then there is the question of dark matter. Most astronomers agree that a true galaxy must be embedded in a halo of dark matter, an invisible component that provides much of the gravitational glue holding the system together. This criterion helps separate galaxies from star clusters, which are usually dominated by normal matter alone. But dark matter cannot be observed directly. Its presence has to be inferred from motion, dynamics, and models. That means classification often depends on indirect evidence rather than clear observation. This leads to objects that sit uncomfortably in between categories. Globular clusters, for example, are dense spherical collections of stars that orbit larger galaxies. Some contain millions of stars, rivaling the smallest galaxies in stellar population. Yet they appear to lack significant dark matter and behave differently from galaxies in important ways. Most astronomers classify them as star clusters, not galaxies, but the distinction is based on interpretation rather than appearance. On the other end of the spectrum are ultra-diffuse galaxies. These objects can be physically large, sometimes comparable in size to the Milky Way, but contain very few stars. Their stars are spread so thinly that the galaxy appears ghost-like, barely visible even with powerful telescopes. In terms of mass, many of these systems are dominated almost entirely by dark matter. They satisfy some criteria for being galaxies, while violating intuitive expectations about brightness and structure. There are also tidal dwarf galaxies, which form from material pulled out during collisions between larger galaxies. These systems can become gravitationally bound and form stars, behaving like independent galaxies. However, they may contain little to no dark matter, challenging the idea that dark matter is a defining requirement. Whether these objects should Be counted as full galaxies or treated as a separate category remains a subject of debate. What makes this ambiguity important is that galaxy counting depends on where these boundaries are drawn. If the definition is too strict, many objects are excluded. If it is too loose, the count swells dramatically. There is no universally agreed-upon threshold that cleanly separates galaxies from non-galaxies in all cases. Instead, astronomers work with a combination of criteria that can produce different answers depending on context. This complexity subverts the expectation that scientific categories are always clean and precise. In many areas of science, definitions are tools rather than truths. They are designed to be useful, not perfect. The definition of a galaxy reflects this reality. It is a practical framework shaped by observation, theory, and convenience, not a rigid rule imposed by nature. The problem becomes even more challenging when distance is involved. Many of the faintest and smallest galaxies are extremely difficult to study in detail. Their motions are hard to measure. Their dark matter content is uncertain. In some cases, astronomers can detect only a handful of stars and must infer the nature of the system from minimal data. Classification under these conditions is necessarily probabilistic. This means that when astronomers talk about the number of galaxies in the universe, they are not counting clearly labeled objects. They are estimating populations based on models, assumptions, and statistical trends. The galaxy count includes many systems that exist near the edge of detectability and near the edge of detect definition. There is an intellectual engagement hidden in this uncertainty. Rather than undermining scientific confidence, it highlights how science actually works. Nature does not always cooperate with human categories. The universe presents a continuum of structures, and we impose boundaries in order to study it. Those boundaries can shift as new discoveries force re-evaluation. Understanding this helps explain why galaxy counts have changed over time. It is not just that we have found more galaxies, 'tis that our understanding of what a galaxy can be has expanded. Objects once dismissed or overlooked are now recognized as legitimate members of the cosmic population. This also reframes the idea of precision. The goal is not to arrive at a single immutable number. The goal is to build a model of the universe that accounts for its complexity as honestly as possible. A galaxy is not a simple thing. It is a dynamic, evolving system that exists within a spectrum of cosmic structures. When you hear an estimate of how many galaxies exist, it carries within it all of these decisions and uncertainties. The number reflects not only what the universe contains, but how we choose to describe it. That choice is guided by evidence, theory, and practicality, not by intuition. Recognizing the ambiguity at the heart of the definition deepens the question. Rather than weakening it, shows that counting galaxies is not a matter of tallying obvious objects scattered through space. It is an exercise in understanding structure, scale, and classification in a universe that resists simple labels. And that resistance is not a flaw in our knowledge. It is a clue to how rich and varied the cosmos truly is. The cosmos truly is. When people they usually think about the giants. The images that circulate in books, documentaries, and online articles almost always feature enormous, luminous systems filled with billions of stars. These galaxies spiral gracefully, blaze with color, and dominate the frame. They look like the main characters of the universe, the cosmic equivalents of capital cities or ancient empires. It is natural to assume that these spectacular objects represent what most galaxies are like. In reality, they represent something very different. Massive galaxies capture attention because they are easy to see. Their sheer brightness allows them to stand out across immense distances. Their structure is dramatic and visually satisfying. They photograph well. From the standpoint of human perception, they feel important. But visibility and importance are not the same thing in astronomy. The universe does not distribute its contents in a way that aligns with what our eyes and instruments find most appealing. Galaxies, like the Milky Way or Andromeda, are impressive, but they are not typical. They are statistical outliers, occupying the upper end of the galaxy mass and brightness distribution. They contain hundreds of billions of stars and dominate their local environments. Yet when astronomers examine the overall population of galaxies, these giants turn out to be rare exceptions rather than the rule. This is where visual bias enters the picture. Our understanding of the universe is shaped by what we can see most easily. Bright objects are detected first, studied most thoroughly, and remembered most vividly. Faint objects are harder to find, harder to study, and easier to overlook. Over time, this creates a distorted impression of what is common and what is unusual. Imagine trying to understand the demographics of a city by only observing the tallest buildings. You would conclude that most people live in skyscrapers, that vast towers dominate daily life, and that small homes are insignificant or non-existent. The conclusion would be understandable, but completely wrong, in much the same way. Focusing on massive galaxies skews our intuition about the universe. Large galaxies do not just stand out visually, they also anchor many of our reference points. When we talk about galaxy rotation, star formation, or black holes, the examples often come from massive systems because they are easier to observe in detail. This reinforces the idea that they are representative. But they are not. They are the bright tip of a much larger and fainter iceberg. The distribution of galaxies follows a pattern where small systems vastly outnumber large ones. For every giant galaxy, there are countless smaller galaxies containing far fewer stars. Many of these systems are so dim that they barely register against the background of space. Some contain only a few thousand stars. Others spread their light so thinly that they are almost invisible, even when their physical size is large. Yet because massive galaxies dominate images and surveys, they dominate imagination as well. They shape the mental picture people carry. When they hear the word galaxy, this creates a subtle expectation that the universe is filled primarily with grand, luminous structures. The reality is quieter and far more uneven. This mismatch between appearance and abundance matters when it comes to counting galaxies. If you extrapolate from what is most visible, you will underestimate the total population. Early galaxy counts fell into exactly this trap. They were based largely on bright, easily detectable galaxies. As a result, they captured only a small fraction of what was actually out there. The giants also give a misleading sense of stability. Massive galaxies tend to evolve more slowly. Their large gravitational wells allow them to hold on to gas and stars over long periods. Smaller galaxies are more fragile. They can be disrupted, stripped, or absorbed by larger neighbors. This makes the universe appear more orderly than it really is if you focus only on its largest inhabitants. There is also a psychological comfort in thinking of the universe as dominated by a few grand structures. It feels more manageable, more symmetrical, more aesthetically pleasing. A universe made mostly of faint, irregular, barely detectable objects feels messier and harder to grasp. But nature is under no obligation to satisfy aesthetic preferences. Astronomers have had to learn repeatedly to distrust their own visual instincts. Each time technology improves and surveys push deeper, the same pattern emerges. The universe reveals more small, faint objects than expected. The population shifts away from the spectacular and toward the subtle. What once seemed like background noise turns out to be the main signal. Understanding massive galaxies as outliers reframes their role. They are not the norm against which everything else is measured. They are the extreme outcomes of cosmic processes, the products of mergers, accumulation, and long histories of growth. Their rarity is part of what makes them interesting. This perspective also creates a productive tension. If the galaxies we see most clearly are not representative, then how much of the universe remains hidden behind the limits of detection? What else is out there that does not announce itself with brightness or symmetry? The giants hint at a deeper population precisely because they stand out so sharply against it. Recognizing visual bias opens a curiosity loop. It invites the realization that the most important features of the universe may not be the ones that first catch the eye. The dominant contributors to galaxy counts are not the objects that dominate images. They are the quiet majority, the faint systems that fill space without spectacle. Once this shift occurs, the question of how many galaxies exist takes on a new dimension. It is no longer about counting the obvious. It is about accounting for what hides in the shadows of observation. The massive galaxies remain fascinating, but they no longer define the universe by themselves. They become signposts rather than representatives. Markers that guide us toward a deeper understanding of cosmic diversity. And in that understanding lies the realization that the universe is not dominated by its most impressive inhabitants, but by its most numerous ones, quietly shaping the cosmos beyond the reach of easy vision. If the universe only by what shines brightest, we would come away with a deeply misleading picture. Beneath the glare of massive galaxies lies a far larger population that rarely appears in images, and often escapes attention entirely. These are dwarf and ultra-faint galaxies, and despite their obscurity, they dominate the universe by sheer number. They are the hidden majority, quietly filling space while the giants steal the spotlight. Dwarf galaxies are small by almost every measure. Many contain only a few million stars, some only a few thousand. Compared to a galaxy like the Milky Way, which holds hundreds of billions of stars, these systems seem almost trivial. Their gravitational pull is weak, their light output is minimal, and their structure is often irregular and messy. From a distance, they fade easily into the background glow of the universe. Ultra-faint galaxies push this trend to the extreme. These are among the dimmest known structures that still qualify as galaxies. Some are so sparse that their stars are spread thinly across space, producing almost no concentrated brightness at all. Others are physically small, compact collections of stars barely held together by gravity. In many cases, astronomers discover them only by noticing subtle motions or faint statistical overdensities in star surveys, not by seeing a distinct glowing object. What makes these galaxies remarkable is not how they look, but how common they are. When astronomers account for observational limits and biases, a clear pattern emerges. As galaxies get smaller and fainter, their numbers rise sharply. For every large, luminous galaxy, there are many more dwarfs. For every easily detectable dwarf, there are likely several even fainter ones that remain unseen. This runs directly against intuition. Human perception is biased toward the obvious. Bright objects feel important. Large structures feel dominant. We instinctively assume that what we notice most must make up most of what exists. In the universe, the opposite is often true. The most numerous galaxies are precisely the ones least likely to announce themselves. Invisibility bias plays a powerful role here. Telescopes have detection thresholds. They can only see objects that emit enough light to stand out against background noise. Dwarf galaxies frequently fall below this threshold, especially at large distances. Their stars are few, their light is weak, and cosmic expansion further dims what little brightness they produce. As a result, vast numbers of galaxies never make it into catalogs simply because they cannot be seen directly. Even when dwarf galaxies are relatively nearby, they can be difficult to identify. Many sit in the halos of larger galaxies, where their Faint light is overwhelmed by brighter neighbors. Others are spread so thinly that they blend into the surrounding star field. For decades, entire populations of these galaxies existed undetected, hiding in plain sight within regions astronomers thought they already understood. This creates an important shift in how galaxy counts are done. Counting dwarf galaxies is not a matter of spotting and tallying individual objects. It requires inference. Astronomers look at the distribution of known galaxies, study how galaxy numbers change with brightness and size, and then extrapolate beyond what they can see. They model how many faint systems must exist to explain observed patterns in galaxy formation and evolution. When this modeling is applied, the numbers change dramatically. The visible galaxies, the ones that populate images and textbooks, turn out to represent only a small fraction of the total. The majority are dwarfs and ultra-faint systems that contribute little light but dominate in quantity. In some estimates, they make up roughly 90% of all galaxies in the observable universe. This is where surprise enters the story. The universe we imagine is not the universe that exists. We imagine spirals and glowing ellipses spread evenly across space. What actually fills most of that space are modest, dim systems that barely register. They are not rare exceptions. They are the standard outcome of galaxy formation. There is also something humbling about this realization. It suggests that the universe is not optimized for visibility or spectacle. Most of what exists operates quietly, without drawing attention. The grand structures that inspire awe are statistical extremes, not typical cases. The cosmic norm is subtle and understated. Dwarf galaxies also play an outsized role in cosmic history. Many formed early in the young universe and later merged together to create larger systems. The Milky Way itself is the product of countless smaller galaxies that combined over billions of years. In that sense, dwarfs are not peripheral. They are the building blocks from which larger galaxies arise. Yet because they are so faint, many of these ancient systems are effectively invisible to us today. Their light has faded, their stars are few, and their signals are easily lost. The universe carries the imprint of their existence in the structure of larger galaxies, but not always in directly observable form. This reinforces a key idea. Absence of evidence is not evidence of absence. The fact that we cannot see most dwarf galaxies does not mean they are not there. It means our instruments and senses are limited. When astronomers say that most galaxies are invisible, they are not making a dramatic claim. They are stating a statistical reality grounded in how matter behaves on cosmic scales. Once this hidden majority is acknowledged, the question of how many galaxies exist takes on a different weight. It becomes less about what we can list and more about what we can infer. The universe is not a catalog of obvious objects waiting to be checked off. It is a population shaped by processes that favor small, faint outcomes over large, luminous ones. There is also a deeper cognitive lesson embedded here. Human attention gravitates toward extremes. We notice the tallest mountains, the brightest stars, the largest galaxies. But reality is often governed by the ordinary and the numerous, not the exceptional. Understanding the universe requires learning to look past what stands out and account for what hides below the threshold of easy detection. Dwarf and ultra-faint galaxies force that lesson upon us. They remind us that the universe is not defined by its highlights. It is defined by its totals. And those totals are dominated by objects that do not impress at first glance, that do not glow brightly in images, and that do not fit neatly into intuition. When astronomers speak of trillions of galaxies, they are not envisioning trillions of majestic spirals filling space with light. They are describing a cosmos packed with small, dim systems, most of them unseen, quietly shaping the large-scale structure of everything we observe. The universe, it turns out, is built not by its showpieces, but by its hidden majority. At a distance, looks orderly. Galaxies appear as distinct islands of stars, separated by vast stretches of space. Each one seemingly easy to identify as a single object. That impression fades quickly when astronomers try to define exactly where one galaxy ends and something else begins. In practice, galaxy classification is not a mechanical process governed by sharp boundaries. It is a judgment call shaped by incomplete information, competing criteria, and objects that refuse to fit neatly into any category. The problem begins with nature's refusal to draw clear lines. The universe does not organize itself into discrete boxes labeled galaxy and not galaxy. Instead, it produces a continuum of structures, ranging from dense star clusters to sprawling systems dominated by dark matter, with many ambiguous cases in between. When astronomers assign names and categories, they are imposing structure on something that is fundamentally messy. Consider globular clusters. These are compact, spherical collections of stars that orbit larger galaxies. Some contain hundreds of thousands or even millions of stars, rivaling the stellar populations of the smallest known galaxies. Visually, they can look similar to ultra-compact dwarf galaxies. Yet most globular clusters appear to lack significant amounts of dark matter and show different internal dynamics. Because of this, they are usually classified as star clusters, rather than galaxies. But that distinction rests on interpretation, not on an obvious physical break. Now consider ultra-compact dwarf galaxies themselves. These objects sit awkwardly between globular clusters and full-size galaxies. They are small, dense, and difficult to study. But evidence suggests that some contain dark matter or represent the stripped cores of once larger galaxies. Whether they should be counted as galaxies depends on which criteria are emphasized: size, mass, formation history, or dark matter content. Different answers emerge depending on which lens is used. At the opposite extreme are ultra-diffuse galaxies. These systems can be enormous in physical size while containing very few stars. Their stars are spread so thinly that the galaxy's surface brightness is extremely low, making detection difficult. Some of these galaxies appear to be dominated almost entirely by dark matter, while others seem to have surprisingly little. They satisfy some definitions of a galaxy while violating others, further blurring the boundary. Tidal dwarf galaxies add another layer of complexity. When large galaxies collide, streams of gas and stars can be pulled out into space and condense into new gravitationally bound systems. These objects can form stars and persist for long periods, behaving much like independent galaxies. However, because they form from the debris of larger galaxies, they may contain little or no dark matter. If dark matter is considered essential to the definition of a galaxy, tidal dwarfs become problematic. If gravitational binding and long-term stability are prioritized instead, they fit more comfortably. Distance compounds the uncertainty. Many of the faintest and smallest systems are so far away that only minimal information can be gathered. Astronomers may detect a faint smudge or a handful of stars and must infer the nature of the object from limited data. Measurements of motion. Mass and composition become uncertain, and classification shifts from determination to probability. An object may be described as likely a dwarf galaxy or possibly a star cluster, reflecting degrees of confidence rather than certainty. This uncertainty reveals something important about galaxy counting. The process is not like counting coins on a table. There is no universal checklist that, once satisfied, automatically increments the total by one. Instead, astronomers rely on models, statistical distributions, and educated judgment. They decide which populations to include based on consistency, usefulness, and the best available understanding of how galaxies form and evolve. This is not a weakness of science. It is a recognition of complexity. In many areas of research, especially those dealing with large, distant systems, categories are provisional. They are refined as new evidence appears and revised when old assumptions no longer hold. The definition of a galaxy has already changed over time and will likely continue to do so. Trust in galaxy counts, then, does not come from rigid precision. It comes from transparency about assumptions and from the robustness of results across different, reasonable definitions. When multiple approaches, using slightly different criteria, converge on similar totals, confidence grows even if no single object can be classified with absolute certainty. There is also a psychological adjustment required here. Many people expect scientific answers to be crisp and final. Ambiguity can feel unsettling, as if it undermines authority. In reality, ambiguity is often a sign that a subject is being taken seriously. The universe is complex, and honest descriptions of it must reflect that complexity rather than smooth it away. Learning to tolerate this ambiguity is part of understanding how astronomy works. Galaxy counts are best thought of as ranges supported by evidence, not exact tallies etched into reality. They reflect what we know, what we can infer, and where uncertainty remains. This perspective reframes the original question. Asking how many galaxies exist is not asking for a perfectly exact number. It is asking how astronomers model a population that spans extremes of size, brightness, and structure, using imperfect data gathered across billions of light-years. The answer, whatever number is given, carries with it a layer of interpretation. It represents a consensus built from many judgments rather than a simple sum. Recognizing this does not weaken the conclusion. It strengthens it by grounding it in the reality of how knowledge is actually constructed in the end. Galaxy counting is less about enforcing strict definitions and more about capturing the richness of cosmic structure as faithfully as possible. The universe resists clean categories, and science advances by adapting to that resistance, not by denying it. Counting not like counting physical objects laid out in front of you. There is no cosmic shelf where each galaxy sits clearly labeled, waiting to be tallied. Instead, astronomers work under strict limitations imposed by physics, technology, and distance. What we see is filtered, incomplete, and biased, not because of carelessness, but because the universe itself restricts what can be observed directly. Understanding those limits is essential to understanding why galaxy counting relies so heavily on inference and modeling. Every telescope has a detection limit. This limit defines the faintest object it can reliably see. Objects brighter than that threshold appear in images and surveys. Objects fainter than it effectively do not exist as far as that instrument is concerned. This is not a sharp boundary. Near the limit, detections become uncertain, noisy, and incomplete. Some objects are seen, others are missed. And the transition between the two is gradual rather than clean. This creates a fundamental observational bias. Bright galaxies are overrepresented because they are easy to detect. Faint galaxies are underrepresented or completely absent because they fall below the detection threshold. The universe does not suddenly stop producing galaxies at the point where telescopes stop seeing them. The visibility cutoff is a property of our instruments, not of reality. Distance makes this problem worse. As galaxies get farther away, their light spreads out over a larger area and becomes dimmer. Even galaxies that would be easily detectable nearby can disappear entirely when placed at great distances. This means that surveys of distant space are biased toward the brightest and most massive systems. The farther we look, the more extreme the visible population becomes. Astronomers are well aware of this bias. The challenge is not recognizing it, but correcting for it. This is where inference enters the picture. Instead of assuming that what we see is all that exists, astronomers ask a different question. Given what we can detect, what must exist beyond our detection limits to make sense of the data? A useful analogy is trying to estimate how many fish live in the ocean using a net with a fixed mesh size. The net easily catches large fish, but allows smaller ones to slip through. If you simply count what you catch, you will conclude that the ocean contains only large fish. A more careful approach recognizes the limitation of the net and uses models to estimate how many small fish must be present based on population dynamics and known patterns. Galaxy surveys work in much the same way. Astronomers measure how the number of detected galaxies changes with brightness. They observe that as galaxies get fainter, their numbers rise sharply, right up until the detection limit cuts the trend off. That cutoff does not represent a real drop in galaxy numbers. It represents the point where the telescope stops seeing them. By studying this trend, astronomers can extrapolate beyond what is visible. They use statistical models grounded in theories of galaxy formation and evolution to estimate how many galaxies must exist below the detection threshold. These models are not arbitrary. They are constrained by observed physics, by simulations, and by consistency across different surveys and wavelengths. Observational bias also comes from the way surveys are conducted. Some surveys cover small areas of the sky very deeply, detecting extremely faint objects, but only in limited regions. Others cover vast areas of the sky, but only detect relatively bright galaxies. Each approach has strengths and weaknesses. Deep surveys reveal faint populations, but may miss rare large-scale structures. Wide surveys capture overall distribution, but miss the faint majority by combining different types of surveys. Astronomers cross-check their results. If independent methods point towards similar conclusions about unseen populations, confidence grows. This convergence is a key source of authority in astronomical estimates. It is not the precision of any single observation that matters most, but the agreement between multiple lines of evidence. Modeling plays a crucial role here. Modern cosmology relies heavily on simulations that start with the conditions of the early universe and follow the evolution of matter over billions of years. These simulations predict how many galaxies of different sizes should form, how they should merge, and how they should be distributed across space. When simulated galaxy populations match observed ones above detection limits, astronomers gain confidence that the unseen portions of the simulations are also realistic. This is a mental reframing that often surprises people. Astronomy is sometimes imagined as a purely observational science, based entirely on what can be seen. In reality, it is deeply inferential. Observation provides constraints, not complete pictures. Models fill in the gaps, guided by physics rather than guesswork. There is also an important distinction between inference and speculation. Inference is disciplined by evidence. It operates within known laws and tested frameworks. Speculation is unconstrained. Galaxy counting relies on inference, not speculation. When astronomers estimate trillions of galaxies, they are not imagining them into existence. They are accounting for populations that must exist for the universe we observe. To behave the way it does, this approach requires trust, but not blind trust. The authority of these estimates comes from transparency and repeatability. Assumptions are stated clearly. Methods are published and scrutinized. Different teams using different data sets and techniques arrive at similar results. Convergence is what gives the numbers weight. Understanding detection limits and observational BIAs also changes how we interpret astronomical images. Images feel like direct representations of reality, but they are curated views shaped by exposure time, wavelength, and sensitivity. They show what can be captured, not everything that is there. The most important features of the universe are often missing from the picture, not because they are insignificant, but because they are subtle. Once this is understood, the reliance on modeling no longer feels like a weakness. It feels like an extension of human perception. Models allow us to reason beyond the immediate reach of our senses, correcting for known biases and limitations. They turn incomplete data into meaningful knowledge. This reframing is essential to the galaxy count question. The number of galaxies we estimate is not a simple tally of visible objects. It is the result of carefully correcting for what we know we are missing. It reflects an understanding of how galaxies form, how light behaves, and how instruments interact with reality. In the end, astronomy does not ask us to believe that what we cannot see exists without reason. It asks us to recognize that seeing is only one way of knowing, and not always the most complete one. By acknowledging detection limits and embracing inference, astronomers transform absence into information. And it is that transformation that makes it possible to speak meaningfully about a universe filled with far more galaxies than our eyes will ever directly reveal. In the mid, astronomers faced a decision that, on the surface, bordered on absurd. They were given access to one of the most powerful scientific instruments ever built, a space telescope orbiting above Earth's atmosphere, free from distortion and light pollution. Time on this telescope was precious beyond measure. Researchers competed fiercely for it, knowing that a single observation could define a career. Every minute was expected to produce clear, valuable data. And then someone proposed using it too. Stare at nothing. Not nothing in a poetic sense, but nothing in the most literal observational sense. A patch of sky with no known stars, no known galaxies, no interesting features at all. Just darkness. From a practical standpoint, the proposal made very little sense. Telescopes were designed to observe objects, not emptiness. The standard approach was to point them at regions already known to contain stars or galaxies, places where results were all but guaranteed. Using days of observation time to look at an apparently blank region felt wasteful, even irresponsible. Many astronomers openly questioned the idea. Why gamble rare resources on a spot that seemed to offer nothing in return? The reasoning behind the gamble, however, was quietly radical. The universe, as understood at the time, was already known to be vast. Astronomers suspected that many galaxies were too faint or too distant to be detected in ordinary surveys. The problem was that no one knew how many were missing. The only way to find out was to push observation beyond the limits of comfort, into regions where intuition suggested there would be nothing to see. The idea was simple in concept, but risky in execution. Instead of scanning large areas of the sky briefly, the telescope would be locked onto a single tiny patch and left there for days. Photons would be collected slowly, relentlessly, accumulating bit by bit. Light too faint to notice in short exposures might gradually build into something detectable. The hope was that darkness itself might reveal hidden structure if given enough time. This approach ran counter to how telescopes were usually used. Most observations balanced depth and breadth, trying to see many objects across a wide area. This proposal sacrificed breadth entirely. It narrowed focus to an almost absurd degree. The chosen patch of sky was so small that if you held a coin at arm's length against the night sky, the observed area would be a tiny fraction of its surface. Critics argued that even if something were found, it could hardly be representative of the universe as a whole. There was also the risk of failure. If the telescope stared for days and still saw nothing, the result would be deeply uncomfortable. It would not just be an empty image. It would be an empty justification. Valuable observation time would be gone, and the gamble would have yielded no return. In a field built on careful planning and incremental progress, this kind of all or nothing experiment was unsettling. Yet that discomfort was precisely the point. The proposal challenged an unspoken assumption that the best way to learn about the universe was to look where something was already known to exist. That assumption had guided astronomy for centuries, but it also carried a hidden bias. If you only look where you expect to find things, you reinforce existing knowledge without testing its limits, staring into empty space was a way of confronting that bias directly. It was a question posed not to the universe, but to the observers themselves. What if the universe was full of things we were missing simply because we never looked deeply enough in the places that seemed uninteresting? As the observation began, there was no immediate payoff. The first images looked exactly as expected: dark, grainy, empty. Each individual exposure showed nothing remarkable. No bright points, no obvious shapes, just noise. If the process had stopped there, the critics would have been proven right. But the exposures did not stop. Hour after hour, day after day, photons continued to accumulate. Images were stacked, aligned, and combined. Gradually, almost imperceptibly, patterns began to emerge. Faint smudges appeared where there had been none. Tiny shapes took form, each barely distinguishable from the background. What had looked like empty space began to resolve into something else entirely. The tension lay in the uncertainty of that transition. No one knew when or if the darkness would give way. There was no guarantee that deeper exposure would reveal more structure rather than simply more noise. Each additional hour of observation carried both hope and risk. When the final combined image was assembled, the result was astonishing. The tiny patch of sky, once thought empty, was crowded with galaxies. Thousands of them, spirals, ellipticals, distorted shapes, all packed into a region so small it defied expectation. Many of these galaxies were incredibly distant, their light having traveled billions of years to reach the telescope. Some were so faint that they had never been seen before and would not be seen again, except through similarly deep observations. The apparent emptiness had been an illusion created by limited sensitivity. The universe had not been sparse in that direction. It had been hiding. What made the discovery especially powerful was not just the number of galaxies revealed, but what that number implied. If a random patch of sky contained thousands of galaxies, then the entire sky must contain vastly more than anyone had previously estimated. The realization did not arrive all at once. It unfolded slowly as astronomers multiplied that tiny area by the full sky and confronted the scale of the result. The decision to stare at nothing had exposed a profound truth. The universe was not just larger than expected, it was fuller. Crowded in places where human perception saw emptiness. The gamble had paid off, but more importantly, it had changed how astronomers thought about observation itself. Empty space was no longer treated as a baseline or a control. It became a frontier, a place where assumptions could be tested and broken. The success of this experiment demonstrated that absence in astronomy often signals limitation, not reality. There is a deeper lesson embedded in this moment. Progress sometimes requires doing something that looks foolish by conventional standards. It requires patience where efficiency is prized, focus where breadth is expected, and faith in method rather than in intuition. The telescope did not discover new galaxies by looking harder at what was already obvious. It discovered them by refusing to look away from what seemed uninteresting. The suspense of that long stare into darkness mirrors a broader scientific truth. The universe does not reveal its secrets on demand. It yields them slowly to those willing to wait, to risk disappointment, and to question whether emptiness is ever truly empty. When the final deep field image was revealed, it did more than impress. It unsettled. Astronomers expected to find something in that patch of sky, but not what actually appeared. The image showed thousands of galaxies packed into a region so small that until then it had been dismissed as empty. This was not a subtle increase over expectations. It was a dramatic multiplication, and it forced a reckoning with how wrong earlier assumptions had been. Each faint smudge in the image represented an entire galaxy, many of them seen as they were billions of years ago. Some were small and irregular, others already surprisingly structured. None of them stood out individually, but together they formed a dense tapestry that rewrote intuition. Space that once seemed sparse was suddenly crowded. The universe, it turned out, was not thinly populated between the obvious landmarks. It was overflowing. The immediate reaction was awe, but awe quickly gave way to calculation. Astronomers knew exactly how large the observed patch of sky was. It was a tiny fraction of the total sky, chosen deliberately to be unremarkable. That choice mattered. Because the region was random, the galaxies revealed there could be treated as representative rather than exceptional. When researchers multiplied that small area by the full sky, the implication was unavoidable. The number of galaxies visible from Earth had to be vastly larger than previously thought. What made this moment so powerful was its clarity. There was no complex chain of reasoning required to grasp the implication. The math was simple. Thousands of galaxies appeared in such a minuscule slice of the sky, then tens of billions had to exist across the observable universe. This was not a speculative leap. It was a direct consequence of what the telescope had seen. For years after, this new estimate became the standard reference. The universe was said to contain on the order of 100 billion galaxies. That number entered textbooks, documentaries, and public consciousness. It already felt impossibly large, far beyond anything humans could meaningfully visualize. Yet, even as it settled into common use, it carried a quiet caveat. These were only the galaxies that could be detected. The deep field images did more than raise the count. They exposed a deeper truth about observation itself. The galaxies revealed were not evenly distributed by brightness. Most were faint, small, and difficult to study individually. The bright, majestic galaxies that dominated earlier surveys were still there, but they were vastly outnumbered. The universe revealed by deep fields was dominated by subtlety rather than spectacle. As additional deep field observations were conducted, the pattern repeated. Each time, telescopes stared longer and deeper. More galaxies appeared. The count rose not because the universe was changing, but because our window into it was widening. What had once seemed like a complete inventory was revealed to be a shallow sample. This realization carried an unsettling implication. If deep fields revealed far more galaxies than expected, then even these images might still be missing the majority. Telescopes, no matter how powerful, have limits. They cannot see infinitely faint objects. They cannot detect galaxies whose light is too spread out, too dust-obscured, or too distant. The deep fields were astonishing, but they were not exhaustive. Astronomers began to ask a different kind of question. Instead of asking how many galaxies they could see, they asked how many must exist for the universe to look the way it does. They examined how galaxy numbers changed with brightness and distance. They studied how galaxies merged over time, how small systems combined into larger ones, and how the population evolved across cosmic history. This shift marked a turning point. The deep field discoveries had shown that direct observation alone was not enough. To understand cosmic abundance, astronomers needed to reconstruct the unseen majority. They needed to infer how many faint galaxies existed below detection limits based on how the visible ones behaved. When this inference was applied systematically, the result was startling. The 100 billion figure, once considered enormous, turned out to be a serious underestimate. Most galaxies had never been counted because most galaxies could not be seen. The universe contained not just more galaxies than expected, but an entirely different distribution than intuition suggested. This was the true payoff of the deep fields. They did not merely add objects to a list, they forced a conceptual overhaul. The universe was not dominated by the galaxies we admired most. It was dominated by galaxies we could barely detect or not detect at all. Brightness had misled perception. Visibility had masqueraded as importance. There was also a profound temporal dimension to this realization. Many of the galaxies revealed in deep fields belonged to an earlier era of the universe. They were small, numerous systems that later merged into larger galaxies. In other words, the universe used to contain even more galaxies than it does today. The present-day galaxy count is the result of billions of years of consolidation. This insight connected abundance to history. Counting galaxies was no longer just about space. It was about time. The number of galaxies depended on when you looked. The deep fields provided a window into a younger universe, one that was richer in small galaxies and more crowded than the cosmos we inhabit now. The sense of awe generated by these discoveries was not fleeting. It deepened with reflection. The idea that what looked like nothing could hide thousands of galaxies challenged a fundamental human instinct. We trust our eyes. We assume emptiness means absence. The deep fields proved that assumption wrong on the largest possible scale. In the years that followed, deeper and more sensitive observations continued to reinforce the lesson. Each improvement in technology revealed more faint galaxies, pushing estimates upward. The universe consistently turned out to be more populated than expected. There was no sign of convergence toward a final, comforting number. The deep field moment stands as a reminder that cosmic abundance is not intuitive. It has to be uncovered patiently, layer by layer, often by doing the opposite of what instinct suggests. Instead of chasing the brightest objects, astronomers learned to linger on the faintest. Instead of scanning widely, they learned the value of staring deeply. That single decision to look at empty space reshaped our understanding of the universe's contents. It revealed a cosmos that is not just vast, but densely inhabited by countless galaxies, most of them humble, distant, and unseen. The revelation was not just numerical, it was philosophical. It showed that the universe is far more generous with structure than human perception ever imagined, and that even the darkest patches of sky can be overflowing with hidden light. For much of modern astronomy, the accepted answer to how many galaxies exist felt surprisingly stable. Ask the question a few decades ago, and you would hear a familiar range repeated with confidence. Somewhere between 100 billion and 200 billion galaxies in the observable universe. The number appeared in textbooks, documentaries, lectures, and popular science writing. It sounded enormous, authoritative, and final. For most people, it already pushed the limits of imagination. Few felt the need to question it. That confidence rested on a chain of reasonable assumptions. Astronomers had conducted large surveys of the sky using the best instruments available at the time. They had mapped galaxy distributions, measured distances, and extrapolated totals from representative samples. The deep field images had revealed thousands of galaxies in tiny patches of sky, and when those results were scaled up, the 100 billion figure emerged naturally. It was not pulled from thin air. It was the product of careful observation and straightforward mathematics. But embedded within that confidence was an unspoken constraint. The count was based almost entirely on galaxies that could be directly detected. That distinction mattered far more than most people realized. The early estimates implicitly assumed that the galaxies we could see represented most of what existed. Faint galaxies were acknowledged, but they were treated as a minor correction rather than a dominant population. This assumption was understandable. At the time, observational data simply did not extend far enough to challenge it. Telescopes had limits, and within those limits, the galaxy population appeared to taper off at the faint end. The trend suggested diminishing returns. It was easy to believe that most galaxies were already accounted for, and that unseen ones added only modestly to the total. Authority reinforced this view. The estimates were produced by respected institutions and published in peer-reviewed journals. They were refined incrementally, but rarely overturned. Each new survey nudged the number slightly higher or lower, but always within the same general range. Over time, repetition hardened consensus into expectation. The universe, it seemed, contained on the order of 100 billion galaxies, and that was that. Yet even during this period of apparent certainty, there were hints of tension beneath the surface. Astronomers studying galaxy formation noticed that theoretical models predicted far more small galaxies than were observed. Simulations of cosmic evolution produced an abundance of faint systems that surveys failed to detect. This discrepancy was often attributed to observational limitations rather than to a fundamental misunderstanding of abundance. At first, these inconsistencies were treated as technical details. Models could be adjusted. Feedback processes could suppress star formation in small galaxies. Detection thresholds could be blamed. None of this demanded a dramatic revision of the total count. The 100 billion figure remained intact, supported by the comforting alignment between observation and expectation. The deeper issue lay in how galaxy populations were interpreted across time. Most early counts treated the universe as if it were static, implicitly assuming that the number of galaxies visible today reflected the number that had existed throughout cosmic history. This assumption simplified calculations, but it glossed over a critical fact: galaxies merge. The universe evolves. The population we see now is not the population that existed billions of years ago. As long as counts focused on present-day galaxies and treated faint populations as marginal, this oversight had little impact. But it became more problematic as astronomers began to study galaxy evolution in greater detail. Evidence accumulated that the early universe was crowded with small galaxies that later combined into larger systems. These galaxies did not disappear. They were absorbed. Their individual identities were lost, but their stars and matter lived on. This realization quietly undermined the earlier estimates. If the universe once contained far more galaxies than it does now, and if many of those galaxies were small and faint, then any count based solely on present-day observations was missing a substantial part of the story. The 100 billion figure was no longer just incomplete. It was conceptually narrow. The problem was not that astronomers had made mistakes. It was that the framework itself needed to expand. Counting galaxies was not just a matter of surveying the sky and scaling up. It required understanding how galaxy numbers changed over time and how many systems existed below detection limits at different epochs. This is where expectation began to reverse. What once seemed like a conservative, well-supported estimate started to look like a lower bound. The question shifted from how many galaxies can we see to how many galaxies must have existed to produce the universe we observe today. That shift in perspective opened the door to a much larger revision. Authority, once a source of reassurance, became a source of reconsideration. The same institutions and researchers who had supported earlier estimates now recognized their limitations. New analyses did not discard old data. They reinterpreted it in a broader context, incorporating galaxy mergers, evolutionary trends, and the steep rise in faint galaxy numbers at early times. This created a moment of cognitive tension for the field. The established number had been repeated so often that it felt almost canonical. Revising it by a small factor would have been unremarkable. Revising it by an order of magnitude was something else entirely. It required astronomers to admit that most galaxies had never been counted at all. Curiosity escalated as the implications became clear. If earlier estimates were missing the majority of galaxies, then the universe was far more crowded than anyone had comfortably imagined. The 100 billion figure was no longer impressive. It was incomplete. The true abundance lay hidden in populations that telescopes could not directly observe and in epochs long past. This set the stage for a major numerical revision, not as a sudden revelation, but as the culmination of growing discomfort with old assumptions. The groundwork had been laid by deep field observations, by simulations, and by studies of galaxy evolution. What remained was to connect these threads into a coherent new estimate. The coming revision would not be based on discovering trillions of new galaxies in images. It would be based on recognizing how many galaxies must have existed. Given what we know about how galaxies form, merge, and fade, it would challenge the comforting idea that the universe had already been mostly catalogued. By the time the revised number emerged, the surprise would not lie in the mathematics. It would lie in the realization that the earlier consensus had been shaped as much by what could not be seen as by what could. The authority that once anchored the 100 billion figure would now support a far larger one. Not because science had failed, but because it had learned to ask a better question. The stage was set for a rethinking of cosmic abundance, one that would force astronomers and the public alike to confront a universe even richer, more crowded, and more hidden than previously believed. When astronomers realized that earlier galaxy counts were missing something fundamental, the question became not just how many galaxies we could not see, but why we could not see them. The answer revealed a layered universe filled with entire populations of galaxies that evade detection for very different reasons. These galaxies are not rare anomalies. Together, they form a vast hidden component of the cosmos, one that reshapes any attempt to understand cosmic abundance. Some galaxies are invisible simply because they are too distant. As the universe expands, light from faraway galaxies is stretched and weakened. The farther a galaxy lies, the more its light is spread out across space and time. Even galaxies that were once bright can fade below detectability when viewed from extreme distances. Their photons arrive sparsely, diluted by expansion, and overwhelmed by background noise. To most telescopes, these galaxies might as well not exist, even though they occupy enormous volumes of space. Distance introduces another subtle effect. Very distant galaxies are seen as they were when the universe was young. Many of them were smaller, less massive, and less luminous than galaxies today. Their stars were fewer, their structures less developed. This combination of youth and distance makes them doubly difficult to detect. They are faint not only because they are far away, but because they had not yet grown into the kinds of galaxies we are used to seeing. Then there are galaxies hidden by dust. Dust is made of tiny solid particles produced in earlier generations of stars. In galaxies that are actively forming stars, dust can be abundant. It absorbs visible light and re-emits it at longer infrared wavelengths. To an optical telescope, such a galaxy may appear dim or invisible. Its stars are there, burning intensely, but their light is muffled behind thick clouds of cosmic debris. This creates a deceptive impression. A dusty galaxy might be forming stars at an extraordinary rate, rivaling or exceeding that of much brighter-looking systems. Yet in visible light, it appears unimpressive or absent. Only when observed at infrared or radio wavelengths does its true activity become apparent. Before astronomers had sensitive instruments in those wavelengths, entire populations of these galaxies went uncounted, quietly skewing estimates of how much structure existed in the universe. Ultra-diffuse galaxies add another layer to the mystery. These systems can be physically large, sometimes comparable in size to well-known spiral galaxies, yet contain remarkably few stars. Their stars are spread so thinly that the galaxy's surface brightness is extremely low. Instead of glowing as a coherent object, the light is smeared across a wide area, falling below detection thresholds even when the total amount of light is substantial. To the human eye, and even to many surveys, these galaxies are almost ghost-like. They do not stand out as objects. They blend into the background, indistinguishable from noise. For decades, astronomers did not realize how common they were. When they were finally detected in large numbers, it became clear that they represented a major class of galaxy that had been systematically overlooked. There are also galaxies that are small to the point of fragility. Ultra-faint dwarf galaxies can contain so few stars that their existence is inferred more from stellar motion than from visible structure. Some are discovered only because a small group of stars moves together in a way that suggests a shared gravitational home. Without careful analysis, these systems would be dismissed as random alignments rather than recognized as galaxies in their own right. Each of these categories reveals a different reason for invisibility. Some galaxies are hidden by distance, others by dust, others by diffuse structure, others by sheer lack of light. None of these factors alone accounts for the missing majority. Together, they explain why so much of the universe remains beyond direct observation. What unites these hidden galaxies is not just faintness, but scale. Individually, many of them are unimpressive. They do not dominate images or headlines. Collectively, they dominate the universe. Their numbers add up quickly, far outpacing the population of bright, easily observed galaxies. The universe, when viewed honestly, is not primarily a place of luminous showpieces. It is a place of subtle systems that accumulate significance through sheer abundance. This realization confronts invisibility bias head-on. Humans tend to equate existence with detectability. If something cannot be seen, it feels less real, less important. Astronomy forces the opposite conclusion. The most consequential populations are often those that lie just beyond perception. What we see most clearly is not necessarily what matters most in the cosmic total. There is also a humbling lesson embedded here. The night sky, even when magnified by powerful telescopes, gives the impression that we are seeing most of what is out there. In reality, we are sampling the brightest peaks of a vast distribution. Beneath those peaks lies an ocean of faint structure that shapes cosmic evolution without drawing attention to itself. As astronomers began to incorporate these hidden populations into their models, the scale of the universe expanded yet again. The question was no longer whether such galaxies existed, but how many of them there were. Estimates climbed as each previously invisible category was accounted for. The total number of galaxies increased not because new objects were suddenly discovered everywhere, but because the blind spots in observation were finally being acknowledged. This process required a shift in mindset. Instead of treating invisibility as absence, astronomers learned to treat it as a clue. Every detection limit implies a population beyond it. Every wavelength reveals something different. The universe does not present itself fully in any single view. It has to be reconstructed by combining partial glimpses across methods, instruments, and assumptions. The scale of what remained hidden was startling. When all these factors were combined, it became clear that the majority of galaxies in the observable universe were not just faint, but fundamentally inaccessible to current instruments. They existed not at the margins of observation, but beyond it. This does not mean they are unknowable. Their influence can be inferred through statistical patterns, through models of galaxy formation, and through the structure of the cosmic web. Their absence from images becomes a form of presence in theory. They leave fingerprints even when they cannot be seen directly. Understanding these hidden populations changes the emotional tone of the galaxy count. The universe becomes less like a gallery of bright objects and more like a layered archive, most of it unreadable at first glance. The galaxies we see are not the whole story. They are the visible fraction of a much deeper reality. When astronomers speak of trillions of galaxies, they are not invoking exaggeration. They are acknowledging that the universe is filled with systems that operate quietly beyond the reach of easy detection. The mystery is not that we cannot see them. The mystery is how much we can infer about them anyway. The hidden galaxies expand the scale of the cosmos in a way that is both unsettling and awe-inspiring. They remind us that the universe is not obligated to reveal itself fully, and that what we perceive as emptiness is often a sign of our own limitations rather than a true absence of structure. One of the most counterintuitive realizations in modern cosmology is that the universe does not contain a fixed number of galaxies. The number we measure today is not the number that has always existed, and it is not the number that will exist in the future. Galaxies are not static fixtures scattered across space. They are transient structures in a universe that evolves, combines, and simplifies over time. When astronomers began to fully account for this fact, it fundamentally reshaped how galaxy totals are calculated. To understand why, it helps to imagine the universe shortly after the first galaxies formed. In its early stages, the universe was denser, more compact, and far more crowded on small scales. Matter had not yet had time to collapse into large, well-organized systems. Instead, it fragmented into countless small clumps. Each of these clumps could form stars and become a galaxy in its own right. The result was a cosmos filled with many small, faint galaxies rather than fewer large ones. These early galaxies were nothing like the majestic spirals we are familiar with today. They were small, irregular, and short-lived as independent entities. Many contained only modest numbers of stars and were highly susceptible to their environments. Gravity, however, ensured that this crowded arrangement would not last. Over time, galaxies interacted, collided, and merged, steadily reducing the total number of distinct systems. This process is not speculative. It is directly supported by both observation and theory. When astronomers look deep into space, they are also looking back in time. At great distances, corresponding to the early universe, surveys consistently show higher numbers of small galaxies per unit volume than we see nearby. As observations move closer to the present day, the population shifts. Small galaxies become less numerous, while large galaxies become more common. The implication is unavoidable. Many galaxies that existed in the past no longer exist as separate objects today. They have not vanished in the sense of disappearing. They have been absorbed. Their stars, gas, and dark matter now reside within larger galaxies. The Milky Way itself is a product of this process. It did not form in isolation. It grew by consuming and merging with many smaller galaxies over billions of years. This merging behavior introduces a crucial correction to galaxy counting. If you only count galaxies as they exist now, you miss the fact that the universe once contained far more of them. A present-day snapshot underrepresents the historical abundance. To estimate how many galaxies exist in the observable universe in a meaningful sense, astronomers must account for this lost population. This is where inevitability enters the story. Given the laws of gravity and the initial conditions of the universe, galaxy mergers were unavoidable. Small galaxies formed first. Larger ones formed later through accumulation. Over cosmic time, the trend is always toward fewer, larger systems. The universe simplifies as it ages, not because matter disappears, but because structure consolidates. For a long time, galaxy counts implicitly ignored this dynamic. They treated the universe as if its present structure were representative of its entire history. That assumption made calculations easier, but it also embedded a hidden bias. It assumed that the number of galaxies visible today approximated the total number that ever existed within the observable universe. Once astronomers began to model galaxy evolution more carefully, that assumption broke down. Simulations that tracked matter from the early universe forward showed a steep decline in the number of galaxies over time. Early snapshots of the simulated universe contained many more small galaxies than later snapshots. When these simulations were compared with deep observations, the agreement was striking. This agreement provided a new lens through which to interpret the deep field images. The abundance of faint, distant galaxies was not just a detection artifact. It was a glimpse into a more crowded past. Each faint galaxy detected at high redshift represented a system that might later merge and vanish as a separate entry in any catalog. Galaxy counting, therefore, had to shift from being a purely spatial problem to a spatio-temporal one. It was no longer enough to ask how many galaxies exist now. The more meaningful question became how many galaxies have existed across cosmic time within the observable universe. When this historical perspective is applied, the numbers increase dramatically. Many galaxies that contributed to the universe's structure are no longer individually identifiable. Yet they must be included if the goal is to understand total abundance rather than present appearance. Ignoring them would be like counting people in a city today, while ignoring all the people who lived there in the past and built it. This reframing also explains why the faintest galaxies matter so much. The early universe favored small systems. Those systems dominate the count at early times. As time passes, their identities are erased through mergers, but their existence is written into the structure of larger galaxies. The stars they formed still shine. The dark matter halos they occupied still shape gravitational landscapes. What is lost is only the label. There is a subtle emotional shift that accompanies this realization. The universe begins to feel less like a static inventory and more like a flowing process. Galaxies appear, interact, and combine. The cosmic population is not stable. It is shaped by time, in the same way biological populations are shaped by evolution. This makes the present-day universe feel quieter than its past. The cosmos we observe now is the outcome of billions of years of consolidation. It contains fewer galaxies than it once did, but those galaxies are larger and more complex. The early universe, by contrast, was busy and crowded, filled with small systems that flickered into existence and were quickly drawn into larger structures. When astronomers revise galaxy counts upward, this historical crowding is a major factor. They are not simply adding invisible galaxies that exist today. They are accounting for galaxies that existed in the past and contributed to the universe we now observe. The total reflects a cumulative history, not a single moment. This perspective reshapes how the question of galaxy abundance should be understood. The universe does not have a single, timeless answer to how many galaxies exist. The answer depends on when you ask and what you choose to count. A present-day census and a historical census will yield different numbers, both correct within their own frameworks. By embracing cosmic evolution, astronomers moved beyond static counting and toward a deeper understanding of abundance. The universe is not just vast in space, it is vast in time. And when time is fully accounted for, the number of galaxies becomes not just larger, but more meaningful. The early universe contained more galaxies than today, not because matter was more abundant, but because it was less organized. Over time, gravity imposed order by reducing diversity of structure. Counting galaxies, therefore, becomes an exercise in tracing how complexity emerges and then simplifies across cosmic history. In this light, the revised galaxy totals are not exaggerations. They are acknowledgments of inevitability. Given how the universe began and how gravity operates, there could not have been only the galaxies we see today. There had to be many more. The universe we inhabit is the product of their gradual disappearance into something larger. And any honest accounting of cosmic abundance must reckon with that crowded, vanished past. Over cosmic time, the universe has a quiet but relentless tendency. It reduces the number of distinct things by combining them into fewer, larger structures. This tendency is nowhere more evident than in the life cycle of galaxies. While galaxies are often spoken of as enduring islands of stars, their existence as separate entities is temporary. Given enough time, gravity ensures that many of them will not remain independent. They will merge, be consumed, or be torn apart, steadily lowering the total count. Galaxy mergers are a natural consequence of how matter is distributed in the universe. Galaxies are not isolated. They live in groups and clusters, bound together by gravity and embedded within massive halos of dark matter. Within these environments, galaxies orbit one another, interact, and occasionally collide. Because space is vast, direct star-to-star collisions are rare. Instead, what collides are gravitational systems. When two galaxies pass close enough, their mutual gravity reshapes both of them. At first, these encounters can be subtle. Tidal forces stretch galaxies, pulling long streams of stars and gas outward. Over time, repeated interactions rob galaxies of orbital energy, causing them to spiral closer together. Eventually, What began as two separate galaxies becomes one. Their stars intermingle, their gas clouds collide and trigger new bursts of star formation, and their dark matter halos merge into a single larger structure. This process is often described as galactic cannibalism, especially when a large galaxy absorbs much smaller ones. In such cases, the smaller galaxy does not survive as a recognizable object. It is pulled apart. Its stars scattered into the larger galaxy's halo, its identity erased. From the perspective of a galaxy count, one galaxy has vanished, even though none of its matter has been destroyed. The Milky Way bears clear evidence of this history. Streams of stars arc across its halo, remnants of smaller galaxies that were torn apart long ago. These stars still exist, but the galaxies they once belonged to do not. The same story plays out across the universe, in clusters where massive galaxies grow by steadily consuming their neighbors. This merging behavior introduces a directional arrow to galaxy numbers. Early in the universe, galaxies were smaller and more numerous. As time passes, mergers become more common, especially in dense regions. The result is a steady decline in the number of distinct galaxies, accompanied by an increase in the average size and mass of those that remain. This trend aligns with a broader principle often associated with entropy. While entropy is commonly described as a measure of disorder in gravitational systems, it manifests differently. Gravity drives matter to clump together, reducing the number of separate structures while increasing their internal complexity. The universe evolves toward fewer, larger systems. Not because it is becoming simpler overall, but because gravity favors consolidation. There is a quiet inevitability to this process. Given enough time, most small galaxies will merge into larger ones. Even the largest galaxies are not immune. Galaxy clusters themselves will eventually merge with other clusters. On the largest scales, structure continues to aggregate. The universe does not preserve individuality indefinitely. This impermanence challenges the way we instinctively think about cosmic objects. We tend to imagine galaxies as long-lived fixtures, static against the background of space. In reality, they are transitional forms. Our identities are temporary solutions to the distribution of matter at a particular moment in cosmic history. Understanding this helps explain why galaxy counts depend so strongly on time. A snapshot taken today undercounts the galaxies that existed in the past and overcounts the stability of those that exist now. Many of today's galaxies will not survive as separate entities into the distant future. Their matter will be redistributed into larger systems, further reducing the total count. This is not a failure of galaxies. It is the natural outcome of gravity operating over immense timescales. Just as mountains erode and continents drift on Earth, galaxies evolve and combine in the cosmos. Change is not an exception. It is the rule. There is also a subtle emotional effect in recognizing this impermanence. The universe begins to feel less like a museum of enduring objects and more like a process unfolding slowly and continuously. Structures form, interact, and dissolve into new forms. Nothing is exempt from this flow, not even the grandest galaxies. Long-term thinking reveals that the present universe is a transitional phase. It sits between a crowded past filled with small galaxies and a future dominated by fewer, larger ones. The number of galaxies is highest early on and declines as cosmic time advances. Any attempt to assign a single, timeless number to galaxy abundance must grapple with this reality. This decline does not mean the universe is losing richness. It is transforming it. Complexity shifts from the number of objects to the internal structure of fewer objects. Large galaxies become more intricate, hosting diverse stellar populations, massive black holes, and complex dynamics. The universe trades quantity for depth. When astronomers revise galaxy counts upward, they are not contradicting this decline. They are acknowledging it. They recognize that many galaxies once existed as separate entities, even if they no longer do. Counting galaxies becomes an exercise in accounting for what gravity has already combined. This perspective reframes the question of existence itself. Does a galaxy stop existing when it merges, or does it persist in altered form? From a physical standpoint, its matter persists. From a counting standpoint, its identity does not. The answer depends on what aspect of reality is being measured. By embracing this ambiguity, astronomers adopt a more honest approach. They accept that numbers tied to evolving systems cannot be static. They reflect processes rather than snapshots. The decline in galaxy numbers over time is not a complication to be ignored. It is a central feature of cosmic history. In the end, galactic mergers remind us that the universe is governed by long arcs of change. What exists now is not what existed before, and it will not be what exists later. Counting galaxies, therefore, is not about freezing the universe at a moment and labeling its contents. It is about understanding how gravity reshapes structure across billions of years. The total number of galaxies declines over time not because the universe is becoming emptier, but because it is becoming more consolidated. The night sky may look calm and timeless, but beneath that calm lies a slow, unstoppable process of combination. Galaxies are born, they interact, and they lose their individuality, contributing to something larger than themselves. And in that quiet impermanence lies one of the most profound truths about the evolving universe. Galaxies do not hold themselves together by the gravity of their stars alone. If they did, many of them would fly apart. This realization emerged gradually, not as a dramatic revelation, but as a persistent mismatch between what astronomers observed and what physics predicted. Stars and galaxies were moving too fast. Galaxies in clusters were behaving as if far more mass were present than could be seen. Something unseen was shaping cosmic structure from the shadows. This unseen component came to be known as dark matter. Not because it is literally dark, but because it does not emit, absorb, or reflect light in any detectable way. It does not glow, cast shadows, or leave visible traces in telescopes. And yet, without it, the universe we observe would not exist in its current form. Galaxies would not have formed as they did. Large-scale structure would not hold together. The cosmic web would unravel. Dark matter reveals itself only through gravity. When astronomers measure how stars orbit within galaxies, they find that visible matter accounts for only a small fraction of the gravitational pull required to keep those stars bound. The same is true when galaxies orbit one another in clusters. The visible mass falls far short. The simplest explanation is that most of the mass is invisible. This invisible mass forms vast halos around galaxies, extending far beyond the regions occupied by stars and gas. These halos provide the gravitational scaffolding that allows galaxies to exist as stable systems. Without them, galaxies would be fragile, transient arrangements easily disrupted by interactions and internal motion. Dark matter is not an accessory to galaxies. It is their foundation. The role of dark matter becomes even more profound at larger scales. Galaxies are not scattered randomly through space. They trace an intricate pattern of filaments, sheets, and voids known as the cosmic web. This structure did not arise from visible matter alone. Simulations show that dark matter collapsed first, forming a hidden framework that guided the later accumulation of gas and stars. Where dark matter clumped, galaxies formed. Where it did not, space remained empty. In this sense, everything visible in the universe is shaped by something invisible. The stars we see, the galaxies we count, and the structures we map all sit atop a foundation we cannot observe directly. This realization carries a quiet, humbling force. It tells us that most of reality is not accessible to our senses, even when amplified by the most advanced instruments we can build. Dark matter also reshapes how galaxy abundance is understood. Because galaxies form within dark matter halos, the number of galaxies is closely tied to the number of these halos. Models of cosmic evolution predict far more small dark matter halos than large ones. Many of these halos may host faint galaxies, or none at all. The visible galaxy population is therefore only a partial expression of a much larger underlying structure. This introduces an important asymmetry. The universe may contain many more potential galaxies than actual luminous ones. Some dark matter halos never accumulate enough gas to form stars. Others form stars briefly and then fade. Still others merge into larger halos before becoming visible at all. From the perspective of gravity, these halos exist. From the perspective of light, many do not. The presence of dark matter forces astronomers to confront the idea that existence does not require visibility. Something can be real, influential, and essential without ever appearing in an image. This runs counter to everyday intuition, where seeing is often equated with knowing. In cosmology, knowing often begins where seeing ends. There is also a deeper humility embedded in this realization. For centuries, humans assumed that the luminous universe was the universe. Stars, planets, and glowing nebulae were thought to make up most of what existed. Dark matter overturned that assumption. It revealed that the familiar world of light is a minority component, a thin layer floating atop a much larger, invisible reality. This unseen majority affects how galaxies evolve and interact. Dark matter halos determine how galaxies move, how they merge, and how they are distributed across space. When galaxies collide, it is their dark matter halos that merge first, setting the stage for the slower interaction of stars and gas. The visible drama of galaxy collisions is guided by an invisible choreography. Accounting for dark matter also complicates galaxy counting. If many dark matter halos host faint or invisible galaxies, then any count based solely on light is incomplete by design. Even if every luminous galaxy were perfectly catalogued, the underlying structure would still be undercounted. The universe would remain richer than it appears. This does not mean astronomers count dark matter halos as galaxies. The distinction remains important. But it does mean that estimates of galaxy numbers are informed by models of dark matter distribution. When astronomers predict how many galaxies should exist, they are really predicting how many halos exist and how many of those halos are likely to host stars. The mystery of dark matter deepens the sense of scale. Not only are there more galaxies than we can see, but those galaxies are embedded in something far more massive and extensive than their visible components suggest. The universe is not just larger in number. It is larger in substance. Dark matter also reinforces the idea that the universe operates on principles that do not cater to human perception. Our senses evolved to respond to light, sound, and touch, not to gravitational influence from invisible particles. The fact that most of the universe interacts with us only through gravity is a reminder that our experience of reality is narrow by necessity. Yet there is also something empowering in this knowledge. Despite being unable to see dark matter directly, humans have inferred its existence through careful reasoning and observation. We have detected its influence across vast distances and timescales. This ability to uncover unseen structure speaks to the power of methodical inquiry over intuition. In the context of galaxy counting, dark matter serves as a reminder that what we tally is always a surface measurement. Beneath that surface lies a deeper layer of structure that shapes everything we observe. Galaxies are not free-floating lights in space. They are luminous expressions of an invisible architecture. This architecture extends everywhere. It threads through clusters, stretches across cosmic voids, and binds the universe together on the largest scales. Without it, galaxies would be fewer, smaller, and more chaotic. With it, the universe becomes a place where structure can grow, persist, and evolve. Understanding dark matter reframes the galaxy question one more time. It is no longer just about how many glowing islands exist in space. It is about how those islands emerge from, and are supported by, a hidden world that vastly outweighs them. The visible universe is not the main event. It is the visible trace of something deeper. That realization invites a particular kind of humility. The universe we see is not the universe that is. It is a partial expression of a reality that remains mostly unseen. Galaxies, for all their grandeur, are surface features on an invisible foundation. When astronomers speak of cosmic abundance, they do so with this unseen scaffolding in mind. The number of galaxies is tied to something far larger than galaxies themselves. It is tied to a universe where most of the matter does not shine, does not announce itself, and does not conform to intuition. In accepting this, the question of how many galaxies exist becomes less about counting lights in the dark and more about recognizing how much of reality operates beyond sight. The universe reveals itself not by becoming simpler, but by becoming deeper. And dark matter stands as one of the clearest reminders that the most important structures in the cosmos are often the ones we cannot see at all. On the largest scales, the universe does not look random. Galaxies are not sprinkled evenly through space like grains of sand. Instead, they trace a vast, intricate pattern that stretches across hundreds of millions of light-years. A structure so large that it can only be seen when many observations are combined. This arrangement is known as the cosmic web, and it reveals that the universe has an underlying order that emerges only when distance and scale are taken seriously. When astronomers map the positions of millions of galaxies, a striking pattern appears. Galaxies cluster along long thread-like filaments that weave through space. These filaments intersect at dense nodes where galaxy clusters reside. Between them lie enormous voids, regions so empty that they contain few, if any, galaxies at all. The result is a network that resembles a three-dimensional web, delicate in appearance but vast beyond comprehension. This structure did not arise by chance. It is the natural outcome of gravity acting on the universe's initial conditions. Tiny fluctuations in the density of matter shortly after the universe began were amplified over billions of years. Regions that were slightly denser pulled in more matter, growing into filaments and nodes. Regions that were slightly emptier lost matter and expanded into voids. Over time, this process transformed an almost uniform universe into one marked by dramatic contrast. The beauty of the cosmic web lies in its scale. Individual galaxies are minuscule compared to the filaments they inhabit. Even galaxy clusters containing thousands of galaxies are just bright knots within a much larger pattern. To grasp the web, astronomers must step back conceptually, abandoning the idea of galaxies as isolated objects and viewing them instead as elements of a grand design. Filaments can stretch for hundreds of millions of light-years, connecting clusters across immense distances. Along these filaments, galaxies flow slowly under gravity, moving toward denser regions. The motion is subtle and unfolds over billions of years, but it gives the universe a sense of direction and flow. Matter is not static. It streams along invisible pathways shaped by gravity and dark matter. At the intersections of filaments lie nodes, the most crowded regions of the cosmos. Here, galaxy clusters form, bound together by enormous gravitational forces. These clusters are among the most massive structures in the universe, containing vast reservoirs of dark matter, hot gas, and galaxies of every size. They act as anchors in the cosmic web, drawing in matter from their surroundings. Between filaments and nodes are the voids. These regions can span tens or even hundreds of millions of light-years and contain very few galaxies. Voids are not completely empty, but their density is dramatically lower than the cosmic average. To human intuition, such emptiness feels unsettling, yet voids are an essential part of the web. They highlight the contrast that gives the universe its structure. There is something profoundly satisfying about this pattern. Humans are wired to seek structure, to recognize order within complexity. The cosmic web taps directly into that instinct. It reveals that even at the largest possible scales, the universe is not chaotic. It follows rules. It organizes itself in ways that can be understood, modeled, and even predicted. This pattern also reframes how galaxy counts should be interpreted. Galaxies are not distributed independently. Their locations are correlated. Finding one galaxy increases the likelihood of finding others nearby, especially along filaments. This clustering behavior means that galaxy abundance is tied to large-scale structure. Counting galaxies is inseparable from understanding where they live. The Webb also reinforces the idea that most of the universe's volume is empty. Voids dominate space, while filaments and clusters occupy a relatively small fraction of the total volume. Yet most of the universe's matter resides in those narrow structures. This inversion, where emptiness takes up space but density holds mass, adds another layer of awe to cosmic architecture. Dark matter plays a central role in shaping this network. Long before galaxies formed, dark matter collapsed into filamentary structures. Ordinary matter followed, flowing into the same gravitational wells. The luminous universe traces the outline of an invisible framework. What we see is the glowing skin of a much larger, unseen skeleton. The realization that galaxies are arranged this way deepens the sense of scale involved in galaxy counting. The universe is not just large because it contains many galaxies. 'Tis large because those galaxies participate in structures that dwarf them by orders of magnitude. Each galaxy is a small part of a much grander pattern. There is also an emotional shift that comes with this perspective. The universe begins to feel less like a collection of scattered objects and more like a living system. Filaments resemble arteries through which matter flows. Nodes act like hearts where matter gathers. Voids provide the space that allows structure to exist at all. The metaphor is imperfect, but it captures the sense of coherence that emerges at scale. This coherence did not require intention or design. It arose from simple physical laws applied over vast distances and times. Gravity, acting patiently, sculpted matter into a network of astonishing complexity. The result is a universe that is both comprehensible and humbling, ordered yet immense. For galaxy counts, the cosmic web provides context. It reminds us that galaxies do not exist in isolation and that their abundance is linked to the distribution of matter on the largest scales. Any attempt to estimate how many galaxies exist must account for this clustering, for the fact that galaxies trace a pattern rather than filling space evenly. The Webb also hints at what lies beyond observation. Filaments extend into regions too distant or too faint to be fully mapped. Voids may contain faint galaxies we have yet to detect. The structure we see is likely only a partial glimpse of a network that extends beyond our current reach. Recognizing the cosmic web amplifies awe, not through sheer size, but through coherence. The universe is not just big, it is structured. It has a geometry that emerges naturally from its origins. That geometry connects galaxies across unimaginable distances, binding them into a single, evolving whole. In the end, the cosmic web transforms the question of galaxy abundance into something richer. It is no longer just about counting lights in the dark. It is about understanding how those lights trace a hidden architecture that spans the universe. Galaxies become markers, illuminating a structure that is far larger than any one of them. Seeing the universe this way invites a quiet reverence. Patterns exist at scales far beyond human experience, yet they can still be understood. The cosmic web stands as one of the clearest expressions of beauty in structure, a reminder that order and complexity can arise without intention, guided only by the steady pull of gravity over cosmic time. Everything we have discussed so far exists within a carefully defined boundary. It is the region of the universe from which light has had time to reach us since the beginning of cosmic history. This boundary, the cosmic horizon, encloses the observable universe. It is vast beyond ordinary comprehension, yet it is not the whole. Beyond it lies a question that cannot be answered through observation alone. How much more universe exists outside our view? The cosmic horizon is not a physical edge. It is not a wall where space ends or where galaxies abruptly stop. It is simply the limit of information. Beyond that limit light has not arrived here, and in many cases, never will. The universe has expanded in such a way that regions beyond a certain distance are receding from us faster than light can cross the gap. Those regions are real, but causally disconnected from us. This distinction is subtle and unsettling. It means there are parts of the universe that exist right now, forming stars, hosting galaxies, and evolving in time, yet they are permanently inaccessible. No telescope, no matter how advanced, will ever see them. The limitation is not technological. It is built into the geometry and expansion of space itself. Once this is understood, the question of galaxy abundance changes again. The numbers astronomers estimate apply only to the observable universe. They describe the contents of a finite cosmic bubble defined by time and light. They do not describe the full universe, because the full universe may extend far beyond this bubble. Cosmological models suggest that, on large scales, the universe is remarkably uniform. The same physical laws apply everywhere. The same patterns of structure formation repeat. If this uniformity continues beyond the observable horizon, then there is no special reason to think our region is unique. The simplest assumption is that what exists here exists elsewhere as well. Under that assumption, the observable universe becomes a sample rather than a total. It is one region drawn from a much larger whole. If trillions of galaxies exist within our horizon, then trillions more may exist beyond it. Repeated again and again across an expanse we cannot measure directly. How large that expanse is remains unknown. It could be many times larger than the observable universe. It could be effectively infinite. Current observations are consistent with both possibilities. The universe could curve back on itself at scales far larger than we can detect, or it could extend endlessly without repeating. From our position, the difference is impossible to determine. This uncertainty invites careful speculation, bounded by evidence rather than imagination. Physicists do not propose infinite universes lightly. They arrive at such possibilities by following equations to their logical conclusions. When those equations do not impose a natural boundary, infinity becomes a mathematically valid outcome. If the universe is infinite, then the number of galaxies is not just large, it is unbounded. There would be no final total to calculate. Any number we give would describe only a fraction, no matter how large that fraction is. Even trillions would be insignificant compared to infinity. If the universe is finite but vastly larger than what we can observe, the conclusion is similar in practice. The total number of galaxies could exceed observable counts by factors so large that they lose intuitive meaning. The observable universe would be a tiny island within a much larger cosmic ocean. This possibility introduces a profound existential tension. Humans naturally seek closure. We want totals, edges, and complete inventories. The idea that the universe may not offer those things is deeply uncomfortable. It suggests that no matter how advanced our science becomes, there will always be questions that remain fundamentally unanswered. Yet there is also a quiet elegance in this uncertainty. It reminds us that knowledge has horizons just as space does. Science does not promise omniscience. It promises coherence within what can be tested. Beyond that, it offers carefully constrained possibilities rather than definitive claims. The notion of a vastly larger or infinite universe also reframes our sense of significance. In an infinite cosmos, any single galaxy, including our own, is not special by position or rarity. It is one expression among countless others. That realization can feel diminishing, but it can also feel liberating. Meaning does not have to come from uniqueness. From a cosmic perspective, the observable universe may be just one region where conditions happen to be right for galaxies to form as they do. Beyond it, the same story may be unfolding endlessly. Or it may vary in ways we cannot currently imagine. Either way, the universe does not revolve around our capacity to observe it. This open-endedness feeds directly back into the galaxy count question. When astronomers say there are trillions of galaxies, they are being precise about a limited domain. They are not implying that this is the final answer. They are describing what can be inferred within the boundaries imposed by physics. The temptation is to push further, to ask how many galaxies exist in total without qualification. Science resists that temptation not out of caution, but out of honesty. Beyond the observable horizon, evidence runs out. Reason can extend possibilities, but cannot confirm them. This leaves the story intentionally unfinished. The universe invites inquiry, but it does not guarantee completion. The cosmic horizon is not just a limit on sight. It is a reminder that reality is larger than any single viewpoint. There is a poetic symmetry in this. As individuals, we live within horizons of experience. We cannot know everything, but we can know something. As a species, we extend that horizon through shared knowledge and careful reasoning. As inhabitants of the universe, we encounter boundaries that cannot be crossed, no matter how far we advance. The question of what lies beyond the cosmic horizon remains open. It is not a gap waiting to be filled with data. It is a feature of the universe itself. Whether the universe is finite or infinite, vastly larger or subtly curved, its full extent lies beyond direct access. And yet, even within that limitation, something remarkable remains true. The observable universe alone contains more galaxies than intuition can handle. It offers abundance beyond emotional comprehension. Whatever lies beyond only amplifies that fact. The cosmic horizon, then, does not diminish the story. It deepens it. It turns the galaxy count into a chapter rather than a conclusion. It leaves us with an open loop, not as a failure of knowledge, but as an honest reflection of how the universe is structured. We stand inside a finite window, looking out into a reality that likely extends far beyond it. The galaxies we count are real, vast, and humbling. The galaxies beyond remain unseen, but not implausible. Between what we know and what we cannot know lies a space where wonder persists, grounded not in fantasy, but in the quiet acknowledgement that the universe is under no obligation to fit within the limits of our understanding. When people hear that the universe may contain trillions of galaxies, the question of life almost always follows. It feels unavoidable. If there are so many galaxies, each containing billions of stars, then surely life must be common. Surely we cannot be alone. This line of reasoning is understandable, but it is also where care is required. The scale of the universe invites speculation, yet scale alone does not provide answers. It provides context, not conclusions. At first glance, the numbers seem persuasive. Vast quantities of stars imply vast numbers of planets. Vast numbers of planets imply vast opportunities for life. This reasoning has an intuitive appeal because it mirrors everyday experience. When conditions are repeated often enough, rare outcomes eventually occur. But the universe does not operate on intuition alone, and life is not a simple outcome of size or repetition. Life, at least as we understand it, depends on a delicate chain of conditions: a stable star, a planet at the right distance, the presence of complex chemistry, long-term environmental stability, the ability to store and transmit information. None of these requirements are guaranteed by the mere existence of stars or galaxies. They are possibilities, not promises. Astronomy can tell us how many stars exist and how common planets appear to be. It can identify potentially habitable environments and study the chemistry of distant worlds. What it cannot yet tell us is how often life actually emerges when conditions seem favorable. That gap is not philosophical, it is empirical. We have exactly one confirmed example of life arising in the universe, and it occurred here. This single data point creates an unavoidable ambiguity. Life on Earth could be the result of a process that is relatively easy and common. Or it could be the result of an extraordinary sequence of events that rarely align. The universe's vastness accommodates both possibilities. Trillions of galaxies leave room for life to be abundant or vanishingly rare without contradiction. This uncertainty is often uncomfortable. Humans are inclined to seek decisive answers, especially to questions that touch on meaning and belonging. The idea that the universe might be filled with life can feel reassuring, a confirmation that we are part of something larger. The idea that life might be rare can feel isolating, even unsettling. Both reactions are emotional responses to a question that science has not yet resolved. Restraint becomes important here. Sensational claims about inevitable life or guaranteed civilizations go far beyond what evidence supports. So do claims of cosmic loneliness, presented as certainty. Honest inquiry sits between these extremes. It acknowledges possibility without insisting on outcome. One of the most important insights provided by galaxy counts is not an answer about life, but a reframing of the question itself. Life does not need to be common to be significant. Even if life arose only once per galaxy or once per 1,000 galaxies, the universe would still contain an extraordinary number of living worlds. Conversely, even if life arose only once in the observable universe, its existence would still be profound. There is also a subtle shift that occurs when thinking about life on cosmic scales. The question moves away from personal relevance and toward philosophical perspective. Whether life is common or rare does not change the fundamental structure of the universe. Stars will still form and die. Galaxies will still merge. Time will still pass. Life, wherever it exists, is embedded within processes that do not depend on it. This perspective can feel humbling, but it can also be clarifying. It removes the need for the universe to validate human existence through abundance. Meaning does not have to be derived from numbers. A single conscious species in a vast universe is not diminished by its rarity, nor is it elevated by imagined ubiquity. There is also the question of detectability. Even if life is common, it may not be easy to find. Civilizations could arise and disappear on timescales that rarely overlap. Technological signatures could be faint or short-lived. Life could exist in forms that do not produce signals we recognize. The silence of the universe, often interpreted as absence, may simply reflect the difficulty of detection across enormous distances and times. This introduces another layer of restraint. The absence of evidence is not evidence of absence, but neither is possibility evidence of presence. The universe does not owe us confirmation. It reveals itself slowly and only where observation allows. Galaxy counts contribute to this discussion by expanding the stage on which life could potentially arise. They do not populate that stage automatically. They remind us that the universe is large enough to accommodate outcomes beyond our current knowledge, both hopeful and sobering. There is also a deeper philosophical implication tied to scale. When the universe becomes unimaginably large, the question of life shifts from "are we alone?" to "what does aloneness mean?" In a cosmos where distances stretch for billions of light years, even a universe filled with life could feel lonely in practice. Connection across such distances may be impossible. Awareness of others may never arrive. In that sense, the emotional impact of life elsewhere is less about numbers and more about proximity. Life could exist abundantly and still remain effectively separate, each instance isolated within its own galaxy, its own epoch. The universe may host many stories that never intersect. This realization encourages a different kind of reflection. Instead of focusing on how many others might exist, attention turns inward, toward the conditions that allowed awareness to arise here. The fact that the universe can produce life at all becomes more striking than the question of how often it does so. Galaxy counts emphasize abundance, but they also emphasize indifference. The universe produces galaxies in vast numbers without regard to whether they host life. Life appears to be a secondary phenomenon, emerging within a system not designed for it. That does not make life insignificant. It makes it fragile and precious. There is value in holding this tension without resolving it prematurely. Existential curiosity thrives in uncertainty. It allows space for wonder without collapsing into fantasy. It invites exploration rather than proclamation. As our instruments improve, we may learn more. We may detect biosignatures in distant atmospheres. We may find evidence that life's chemistry is widespread. Or we may discover that life is extraordinarily rare. Each outcome will reshape understanding. But none will negate the vastness of the universe itself. For now, the responsible position is patience. The universe has revealed its size, its structure, and its history. It has not yet revealed how often it gives rise to life. The galaxy count expands the context for that mystery without solving it. In that way, the question of life mirrors the question of galaxies. Both resist simple answers. Both force us to confront the limits of intuition. Both remind us that understanding does not always arrive as certainty, but as a clearer picture of what we do not yet know. The universe may be filled with life, or it may be nearly empty of it. What is certain is that it is large enough to contain either truth without contradiction. And in that vastness, the fact that we can ask the question at all remains one of the most remarkable outcomes the universe has produced. When all the numbers are set aside, when the models, estimates, and revisions are stripped back to their core, what remains is not a final answer, but a story. Counting galaxies turns out not to be a quest for closure, but a record of how far human curiosity can reach into a universe that does not yield itself easily. The question was never really about arriving at a number that feels satisfying. It was about learning how to ask better questions in the face of overwhelming scale. From the beginning, the act of counting galaxies has pushed against the limits of perception. Each step forward has revealed not only more of the universe, but more about ourselves. We learned that our intuition breaks down at large numbers. We learned that seeing is inseparable from time. We learned that most of what exists does not announce itself with light. And perhaps most importantly, we learned that understanding does not require emotional comprehension to be meaningful. The universe did not gradually reveal its abundance because it wanted to be known. It revealed it because humans kept looking, kept refining methods, kept questioning assumptions that once felt sufficient. Each revision of the galaxy count was not an admission of error, but a sign of growth. The universe did not change. Our ability to describe it did. There is a temptation, when faced with immense scale, to search for finality, to want the last word. A number that can be written down, memorized, and treated as complete. But the history of galaxy counting resists that impulse. Every time the story seems settled, new evidence widens the frame. New instruments reveal new populations. New perspectives expose old blind spots. The universe remains one step ahead, not out of spite, but because it is larger than any single method of knowing. This is not a failure of science. It is its defining strength. Science does not promise certainty. It promises coherence. It builds understanding that can adapt as new information arrives. The galaxy count is a living number, shaped by evolving knowledge rather than fixed truth. It reflects an ongoing conversation between humanity and the cosmos, not a completed inventory. Seen this way, the trillions of galaxies are less important than the process that revealed them. What matters is that beings on a small planet, orbiting an unremarkable star, develop the capacity to infer the existence of structures billions of light years away, structures they will never visit. Structures whose light began its journey long before humans existed. The fact that this is possible at all is extraordinary. There is also something quietly grounding in the absence of certainty. The universe does not collapse into meaning simply because we name its contents. It remains vast, layered, and partially hidden. The lack of a final answer leaves room for humility, a recognition that knowledge is always provisional and perspective-bound. This humility does not diminish human significance. It reframes it. Meaning does not arise from dominance or completeness. It arises from participation, from the act of observing, questioning, and refining understanding in a universe that does not center us, yet still allows us to understand it in part. Galaxy counting becomes, in this light, a story about awareness, about the universe reaching a point where it can look back on itself, however imperfectly. Every estimate, every revision, every deep field image is part of that self-reflection. Not because the universe intends it, but because the processes that shape stars and galaxies also, in rare cases, produce minds capable of curiosity. There is a poetic symmetry here. The same gravity that gathers matter into galaxies also gathers questions into understanding. The same expansion that carries galaxies apart also expands the boundaries of knowledge. The universe does not pause for us, but it leaves traces that can be followed, patterns that can be decoded, histories that can be reconstructed. Ending this story with a number would feel incomplete, because numbers alone do not capture what has been gained. Whether the observable universe contains 2 trillion galaxies or more, that figure will likely change. It will be refined, challenged, and contextualized by future discoveries. New telescopes will peer deeper. New methods will correct old assumptions. The horizon of knowledge will shift again. What will remain constant is the posture of inquiry, the willingness to accept that some questions lead not to answers, but to better ways of thinking. The galaxy, it invites awe, but resists spectacle. It expands imagination without promising resolution. There is continuity in this openness. The universe does not end where our knowledge ends. It continues beyond our horizon, beyond our instruments, beyond our lifetimes. And so does the process of understanding, carried forward by generations who inherit questions rather than conclusions. In that sense, counting galaxies is less about measuring the universe and more about locating ourselves within it. Not at the center, not at the edge, but somewhere in between. A place where curiosity arises naturally, where questions persist, and where answers are always provisional. The night sky still looks quiet. Even knowing what lies behind it, most of it remains invisible. The stars appear unchanged. The darkness feels the same. Yet beneath that familiar view is a reality of staggering abundance, shaped by forces indifferent to observation, yet accessible through thought. That tension between indifference and accessibility is where wonder lives. The universe does not care whether we understand it, but it allows understanding anyway. It offers just enough evidence to reward patience, just enough mystery to prevent complacency. So the story does not end with a final tally. It ends with an invitation to keep looking, to keep questioning, to accept that knowledge grows not by arriving at certainty, but by learning how to live comfortably with its absence. The galaxies we count today are markers along that path. They tell us how far we have come, not how far we can go. Beyond them lie more galaxies, more questions, more unseen structure. The universe remains open, not because it is unfinished, but because understanding it is an ongoing act. In the end, galaxy counting reveals something quietly profound. The universe is vast enough to overwhelm intuition, yet structured enough to be understood in fragments. It does not resolve into a single, comforting picture. It unfolds gradually, offering insight without closure. And perhaps that is the most fitting conclusion. Not certainty, but continuity. Not an answer, but a deeper appreciation of the questions themselves. The universe continues to exist. Galaxies continue to form and merge, and human curiosity continues to reach outward, tracing faint patterns of meaning across an expanse that will never be fully known, but will never stop inviting understanding.